Let's take a look at an example of using data to figure out the rate law for a reaction as well as a few other things. For this reaction, we're combining chlorine and water to make hydrochloric acid and hypochlorous acid. And we want to determine the rate law. We want to determine K, and then determine the rate when we have some given concentrations. And of course, it may be tempting to say, well, the rate is simply Cl2 to the first power and water to the first power, and we're done. Incorrect. Don't do that. Rate laws must always be determined from data. And so, we have the data. Here it is. So, some experiments were done, concentrations were measured, as well as the rates of the reaction, the initial rate. So, we know that we have this general form of our rate law. We know that it's equal to the rate constant times first reactant to a coefficient and second reactant to another coefficient. Remember that we cannot get these directly from an equation necessarily. We have to get them from the data. And so with this, you want to compare pieces of data where only one thing is changing. For example, between experiments 1 and 2, chlorine's concentration changes, but water doesn't. So that's a good comparison. Between experiments 2 and 3, though, both chlorine and water are changing. And so that would not be a good comparison to make. However, 1 and 3 would be, because in that case, chlorine isn't changing, but water is. So we always want to look for two sets of data. One set has your kind of baseline values, and then your second set should only change one of those concentrations. And so it would be a good idea to compare 1 and 2, as well as 1 and 3 in this case. Don't compare 2 and 3. So if we do that, we can say that the rate for number 1 is 4 times 10 to the negative 5. Remember, when we're comparing, we can just get rid of K. We've got 0.100 to the m power, 0.100 to the n power. So we need to put our fractions in. So if we're going to compare with the second data set, we have 16 with 10 to the negative 5. We have 0.200 to the n power and 0.100 to the n power, so those cancel out. And so again, that's why you want to select data sets that have one of the reactants staying the same. In doing so, we get 1 over 4 equals 1/2 to the n power. And so solving this, we get m equals 2. And again, if you really wanted, you could mathematically plug these into a calculator, but hopefully we know that 4 over 16 is 1 over 4. And that 1 over 2 is 1/2. Or sorry, 0.1 over 0.2. All right, so we figured out our coefficient for, or our exponent for chlorine. Let's do the same for water. So let's compare experiments 1 and 3, where water changes but chlorine doesn't. And if we go ahead and do that, 4.0 times 10 to the negative 5 over 4.0 times 10 to the negative 5 equals 0.1 to the m, 0.1 to the m. Technically, we can plug in m if we really wanted, because now that we solved for it, but it's going to cancel out anyway, so why bother? And our waters are 0.1 and 0.2. Now that we have everything, the m's cancel. We see that we have 1 equals 1/2 to the n power. So what does n have to be? Only one thing will give us 1, and that would be if n is 0, right? Anything to the 0 power is 1. So in fact, our rate law for this is going to be K times Cl2 squared times H2O to the 0 power, or more likely, or better yet, we can just get rid of it. So our rate law is simply KCl squared. Cl2 squared, rather. So this reaction is second order in respect to chlorine, it's 0 order in respect to water, and it's second order overall. And now with that, we can go ahead and figure out our rate law. So we can figure out our constant. So if we know that our rate is KCl2 squared. We can just choose any of the data sets, doesn't matter. I'm going to just choose rate data set 1. So 10 to the negative 5th meters molar per second is 0.1 molar squared times K. I'll put K in front because we'll be consistent there, my mistake. In doing so, bust out thy calculator. Actually, this one we hopefully don't need to do. We should just get 4 times 10 to the negative 3rd power. And in this case, we have negative molar and negative 1 seconds as our units. And if we're doing correct sig figs, we should only have 2. And so we have 4.0 times 10 to the negative 3rd per molar per second. And the last question was to find out the rate when we have given concentration. So Cl2 is 0.1, H2O is 0.05. We saw that the 0.05 doesn't matter, but let's go ahead and see how to do that. So our rate is going to be K times Cl2 squared. So we don't need the water concentration at all. We know K is 4.0 times 10 to the negative 3rd per molar per second. And our concentration of chlorine is 0.100 molar. We've got to square that. And as expected, with any of the data points we saw that when chlorine was 0.100, we had 4.0 times 10 to the negative 5th. And indeed, the math works out that way. So we have figured out the same thing as before. We have just demonstrated that the water is not affecting our rate here. So at any time for this particular reaction at this particular temperature, when chlorine's concentration is 0.1 initially, we should start with an initial rate of 4 times 10 to the negative 5th molar per second. Right? And so that's how we'll approach problems like this.